NCTSPM, our National Center Seminar Series, and we are very pleased to have a good friend and colleague among us today. Our speaker is Professor Chandra Bhat. He is the Director of the Center for Transportation Research at the University of Texas at Austin. He has been at the University of Texas at Austin for nearly 20 years and has been a faculty member there and guided many students on to successful careers of their own. Recently took over as the director of their center, and Dr. Bhat is most renowned and world-renowned for all his work in the travel behavior modeling field, with a focus on a lot of methodological developments in transportation systems modeling, travel behavior analysis, and develops new econometric and statistical methodologies so we can get deeper insights into travel behavior. Dr. Bhat has been a close friend and colleague for many of us, including Bhat and myself and several of you over the years. So we are absolutely delighted to have him here, and Rory as well. And, so thank you for coming. And I'm not going to belabor with a long introduction. I will just pass it on to Dr. Bhat.
Thank you. Always a pleasure. As Ram indicated, it's been a long journey for many of us, and we still see a long road ahead of us. Still young, but these friendships that have developed, I treasure them, and I certainly look forward to continuing the collaboration between all these. So with that, I'd like to talk some about cause-effect relationships in multidimensional integrated models. I'd like to acknowledge my co-author, Sebastian Astroza, who is a PhD student. Also, Aarti Bhat, who is, yes, my daughter, who is pursuing her undergraduate in the area of human development, not very far away from some of the work that we do. And Ty Nagel, who is a professor at Technique University in Berlin. And this work is supported by a US DOT fund, a grant, and a Humboldt award. So I have to say that this whole area of cause and effect, one could write, still write, there have been many books on this topic. It's very philosophical when you think about it. What is a cause? What is an effect? I won't dwell too much from that philosophical angle, though I might come back to it from time to time. My daughter teaches me quite a bit about cause and effect. She is, I think she's got a very good acumen of observing, analyzing, and part of what she does today in her human development program is watch kids. She has to do that, and then observe kids and have a record of potential cause effect. Okay? You know, this kid was seen this way, this is the effect. You know, she or he behaved in specific ways, or someone taunted a kid, and how did the kid react? So you know, she does a lot of that. I do recall many years back, very enlightening, simple thing but quite enlightening. She sustained an injury of some kind, and she was all in tears, and came home and gave her some nice chocolate, right? So in her terms, she sustained a boo-boo, and she got a chocolate. Right? And then many months later, I gave her a chocolate, and her first question was, but where is my boo-boo? Okay, so I mean, quite interesting, the whole concept of cause and effect. In some ways, it is straightforward. In some cases, it's straightforward. Yeah, at least you think it's straightforward, and you start peeling the onion, and it becomes trickier and trickier. But in general, it is more straightforward when the cause and effect have a very short temporal span, or are within a very short temporal span of each other. Okay. In many of the cases, like the ones that we're going to talk about, if I make a change to a built environment element, okay, it takes a whole long time for potentially some of that effect, some of the effects to be manifested. And as the time frame starts to expand in terms of potential repercussions of a cause, it becomes extremely difficult to understand what is a cause, what is an effect, what are the intervening issues and factors. So by no means am I here to say that we know how to disentangle these relationships, but it is a very active area of research that my friends over here, both Ram and Bhat, have also contributed quite substantially. So with that as an introduction, so integrated modeling is basically to acknowledge the joint nature of decision making relevant to interrelated outcomes. And jointness may arise because of the impact on the multiple outcomes of common underlying exogenous observed variables or unobserved variables, or the combination of both. And in almost all cases, it's some combination of the two. An example would be residential location, auto ownership, and activity time use. So the point is, households with very low income earnings may choose to or may be constrained to locate in high population density areas, okay, perhaps less expensive housing. Okay. But they also, because of their low income earnings, may be likely to own fewer vehicles and may spend less time in recreational episodes. Okay. Now, if the jointness that we see among the outcomes of residing in a high density neighborhood, low household auto ownership, and less time in recreational episodes, if the jointness is purely because of income, then modeling is quite straightforward. All that you have to do is you have to control for income earnings in all the three equations, and independently you can model the outcomes. Okay, no problems there. Now, things get trickier if you start having unobserved factors. So, for example, if an individual is intrinsically dynamic, and in surveys or in some other observation mechanisms, I do not observe this dynamic characteristic, or even this active gung-ho lifestyle, then individuals with these characteristics may in fact reside in high density areas because they want to participate in a lot of activities, active lifestyle, own fewer autos, and invest substantial time in running, recreational pursuits, etc. Okay? And so when you have such unobserved factors that can affect the multiple outcomes, then things become a little tricky. And not only tricky, but also the issue of jointness becomes germane to policy considerations, as I'll talk a little more about later on. So in this situation, independently modeling the various outcomes can lead to inefficient estimation of covariate effects. Inefficient in the context of econometrics here, in the sense that I'm not extracting the information on other outcomes when modeling one particular outcome. And there's a lot of literature on this. What is quite surprising is there's less discussion, not in the econometrics. In the econometrics literature, this is very well known. But surprisingly, in the statistical literature, okay, the reason for joint modeling is pretty much focused on efficient estimation. Okay. There's not much discussion of this notion that if you want to have one outcome potentially be a determinant of another outcome, and if you don't take the jointness into account, that could corrupt the impact of one outcome on another. So that is, from an econometric perspective, inconsistent estimation. Okay, so the literature is dominated by the joint modeling of multiple continuous outcomes. So, this is standard classical simultaneous equations models today in any econometric textbook you take. If the outcomes are continuous, reasonably straightforward, and you also have less issues related to identification of parameters. But what happens when outcomes are non-commensurate? And this is where when I say non-commensurate, mix of continuous and discrete variables of different types. Okay? So even within discrete, you could have multiple types of discrete variables. The problem arises because you are not able to connect the multiple outcomes using a joint multivariate distribution directly on those observed outcomes, as we are able to do in the case of continuous outcomes. Okay? That's where the problem starts to come in. Now, what I'd like to talk a little bit about in this presentation is, what if the dependent outcome is for multiple discrete continuous nature? For reasons of time, I won't be able to go into the details of this multiple discrete continuous modeling mechanism. There are papers that I have in 2005 and 2008 that talk about the basics of the multiple discrete continuous model. As has been, this whole thing was started by Honeyman in his dissertation years back, but in 2005 and 2008, through some nice assumptions, convenient assumptions on certain stochastic terms, I was able to develop a closed form probability model for a multiple discrete continuous case. But the point here is, how can I incorporate such a multiple discrete continuous variable within a larger spectrum of other outcomes? So I'll talk a little bit about multiple discrete continuous in just a bit. Not much. So the current paper, we have a new approach for the estimation of joint mixed models that include an MDC outcome, a nominal outcome, as well as count, binary, as well as continuous outcomes. And the point is, we specify for the non-continuous variables, we specify latent underlying unobserved factors and generate jointness among the outcomes by in some way tying the latent variables that technically get manifested in the form of the observed non-continuous variables. But by having continuous distribution or continuous variable underlying the non-continuous observed variables, we are then able to come up with multivariate distributions. Okay? And reported subjective attitudinal indicators for the latent variables help provide additional information and stability. Now, these attitudinal indicators are not needed, okay, but they can help if you have them. And we apply that to the analysis of residential location choice, household auto ownership, commute distance, and time use choices. And it's the reason will become obvious why we want to focus on joint modeling of these. So the residential location choice we consider as a nominal discrete choice with 4 land use density categories based on housing unit density. The continuous outcome is average commute distance in the household. The reason why we pick these two for residential location choice is the combination of the two can help circumscribe in a downstream actual residential choice model the choice set. Okay? And these two are important factors that are considered in residential choice. Generally the density, but also the average commute distance. And when I say the average commute distance, this model is at a household level. So I'm taking the average of the commute distances across all workers in the household. Note, yes, the assumptions as in any other model, I'm assuming that the employment choice and the work location choice precedes the home location choice. Household auto ownership is a count outcome, and individual activity time use in non-work activities is the MDC outcome. So I'm looking at a day, and in the day, there might be multiple activities that I might participate in, which are all non-work. Okay? So I might go to the gym, I might watch some TV, I might socialize. Okay? So these are all multiple alternatives of activity purposes, and I might participate in multiple of them as opposed to a single one. And obviously I have a limited time budget. And so I invest different amounts of time on these different activities. And that is the MDC part, which I won't talk too much about. but in terms of the mechanics of the model. So, to our knowledge, this is the first formulation and application in the econometric and statistical literature that incorporates an NDC outcome along with all the other outcomes into a single framework. And we also estimate the model not through the traditional maximum likelihood or maximum simulated likelihood or other methods. We have different methods of estimating the models. Okay, so mixed modeling, the term that's used for this kind of modeling is mixed modeling in the statistical literature. Okay? And clearly this is spurred by high dimensional data that we get from different types of sensors today. Okay? And so in the statistical field, you have all kinds of acronyms for these models: GLOM, CTCM, GMDM. They're all there in the paper that I just completed. I'm not sure I can myself recall what those acronyms stand for. Suffice it to say, we have all of these different types of models. In the economics and transportation fields, for a long time in the statistical field, they didn't include nominal variables. Okay? But in the transportation field, we deal quite a bit with nominal variables. So nominal variables were included, not necessarily in conjunction with the other variables. And the social science field, the whole area of structural equations models has been in existence for years. And the point is you generate dependence using latent psychological constructs. And if those psychological constructs impact multiple outcomes at the same time, we have created joints. Especially if those latent constructs are considered stochastic by themselves. Okay? So you have this whole area of structural equations models. Interestingly, the structural equations models, even to this day, if you look at strata, S-class, whatever, they do not do complete justice for even nominal variables. The way they include nominal variables is technically not through the latent variable construction of the nominal variables, but through logistic link functions, okay, which really confines the modeling into very simple nominal forms such as the multinomial mode. Now in the transportation field, some of you might be aware there's something called ICLV, Integrated Choice Latent Variables. And that whole model is really based on the SEM, but it focuses almost exclusively on nominal variables. Okay? But it goes with the idea of a latent psychological construct. And the SEM and the ICLV, by the way, the SEM generally uses multivariate normality for all the stochastic terms. The ICLV, for various reasons, for whatever reasons, started off with a kernel term that is logistic and does some integration, etc. Not the best, in my opinion, of how the ICLV should have been developed in the first place. And so a few years back, we came up with another formulation for ICLV that we just felt fit much better and was much easier to estimate. So, in a paper about a year back, I talked about, another acronym, GHND, which kind of combines the SEM method with the ICLV method. It's general enough to accommodate other models, and it allows for multiple nominal variables, multiple ordinal variables. So primarily it is an SEM, but allowing for multiple nominal variables also, and the nominal variable can be modeled using literally any form you would want to use in the context of the simple nominal output. And this is an estimation approach that we have been using quite substantially, what we call the maximum approximate composite marginal likelihood, or the MAP-ML approach. Again, in this presentation, I won't be able to go into the details of this approach, but the cool thing about this approach is that it allows for joint estimation, and at the same time it's very tractable, computationally convenient, and we have shown even in simple univariate mixed logit or multinomial probit cases, it just beats the MSL hands down. So no comparison with current ways of simulating these models. Now, from an empirical context, let's talk about cause-effect relationships. Should end at about 50?
Yeah,
45?
I'll let you know when you have my 5 minutes.
Okay. So, cause-effect relationships. When you look at cause-effect, it seems like if 3 criteria are met, you can say that a cause has an impact, and there's the effect. Okay. So, the first criterion is once again, it's obviously temporal precedence of the cause. The cause should have preceded the effect. Okay. Quite straightforward it seems, directionality as I call it. The second is, whenever cause happens, so should effect. Okay. It's a relationship. Now, I can generalize this to more of a stochastic trend. So it need not be that whenever cause happens, the effect should happen, but whenever the cause happens, the effect tends to happen. I tend to observe, so I introduce some stochasticity. Okay. But that's the second criterion. Whenever cause happens, so should effect, which means the inverse too. Okay? When cause does not happen, we should not see the effect. That's a relationship. Okay? That establishes the relationship. And then you have no other factors can explain the covariation. This is perhaps the most tricky of all. Okay. The first two, in some circumstances, it's quite easy. Right? A child is hungry, she or he cries. Okay. If you can see